Today we study ESA12H, partial differentiation in physics. The kinetic energy of a particle of mass m is given by 1/2 mass times the velocity squared. Here, x is the position of a particle of mass m. This x dot square is a scalar product between the velocity and itself. If I make use of Cartesian coordinates, we know EI dot EJ equals canonical delta IJ. That is 1 for I equals J and 0 if I is not equal to J. Therefore, only the diagonal component for this square survive, and kinetic energy is 1/2 mass and speed squared, the velocity squared, that is sum of the square of Cartesian coordinates of velocities. We can compute the partial derivative of this kinetic energy with respect to the x component of the velocity, that is x1 dot. For simplicity, if I replace this one x1 dot by a and x2 dot by b and x3 dot by c, then this kinetic energy is 1/2 m a squared b squared plus c squared. So partial derivative of the kinetic energy with respect to the x component of the velocity is something like this after replacing these xi dots with a, b, and c. So this one is nothing but 2 times a, and cancel ma, and a is, let us return to the original expression, mass times velocity along the x-axis. In a similar manner, kinetic energy is a partial derivative with respect to the ith component of the velocity is a mass times ith component of velocity. We call this one mass times velocity to be the linear momentum. Linear momentum of the particle. So we can make use of chain rule. What we have done is a chain rule. X, F, O, F. If I have a function of x, if I know the derivative of this, what happens to the case f squared of x derivative? This one is, first, take the derivative with respect to f, and then take the derivative of f with respect to x. So this is very convenient. It becomes a very convenient, easily understood if we apply this Leibniz expression, Leibniz notation for the derivative. It's much better than Newtonian definition of dots. Sometimes the dot is very useful, but the differential D operator is very convenient to compute. Anyway, the kinetic energy is a partial derivative with the Cartesian components of the velocity is the linear momentum, and this is a vector quantity. By applying the chain rule, okay, we know this kinetic energy is a function of x1 dot, x2 dot, and x3 dot. I'd like to know the total differential. What happens to this function when all of the variables are varied from an original value to another. So x1 becomes x1 dot plus some differential. x2 dot is x2 dot plus differential, something like that. So in that case, we apply the chain rule for multivariable. We recall that function of f is a derivative, something like that. Okay? So f equals x squared. Then its a derivative is 2x. So this one can be written in the form df equals 2x dx. Okay? This is another way to express the derivative. In this case, we have a single variable, but here we have three variables that contribute to the change of the kinetic energy that are x1 dot, x2 dot, and x3 dot. Therefore, it's a partial derivative multiplied by the differential of x1 dot and 2 and 3, sum of them. We recall that the partial derivative of the kinetic energy with respect to the Cartesian component, a single Cartesian component of the velocity, is the linear momentum. So I can copy this. Finally, we can find it's nothing but the scalar product between these two. All right. Let's come back to the original form for the kinetic energy. It was x dot squared. That was the scalar product. Okay. So Leibniz rule for the differential of the product is a times differential of b plus b times differential of a. We can make use of this relation to this. Why? X dot vector squared is x dot dot x dot. And we'd like to compute the differential of this. And these are sum of, this is a sum of x1 dot plus x2 dot x2 dot x3 dot x3 dot differential. Therefore, if I substitute a for b, we have dA squared is 2a dA. In a similar manner, they are all 2x1 dot dx1, 2x2 dot dx2, plus 2x3 dot dx3 dot. And this is a scalar product, so it is 2 times x dot dot dx dot. This is the result. Okay, so we can directly compute this. This one is 2 times x dot dx dot. As a result, m velocity, scalar product, the differential of the velocity. Next, we consider the potential energy. Potential energy U is defined by, this is the value at a reference point that is called x0, subtracted by please remember the negative sign subtracted by an integral. This integral is force times, this is a scalar product, and the displacement, infinitesimal displacement. This one is integrated from the reference point to an arbitrary point, and the value at x is on the left-hand side. So this value, potential energy at a reference point, is a free parameter. So we can choose this number an arbitrary value. So it is not fixed one. The infinitesimal change in the potential energy accompanied by the displacement from x to x plus dx at some point x to a tiny shift from this to there. So change this differential. So this is constant. Constant differential is absolutely zero. And differential of integral is just integrand multiplied by the infinitesimal differential of the variable. And we have negative sign here. Again, we find this a scalar product. Scalar product. So we can express each vector as a linear combination of the three Cartesian coordinates. Finally, they are sum of the differentials along the x-axis, y-axis, and z-axis. On the other hand, we recall this relation, chain rule for multivariable. We assume that the potential energy is a function of position only, and we assume it is independent of velocity. If it depends on the velocity, the story becomes very complicated. So it appears in the electromagnetism, but we are not familiar with the very complicated electromagnetism. We restrict ourselves to the velocity-independent force only. In that case, the potential energy, the force is independent of velocity, and force is depending on the position only. As a result, the potential energy and its differential depends only on the coordinates, Cartesian coordinates, x1, x2, and x3. So applying the chain rule for the three variables, x1 and x2 and x3, our total differential of the potential energy is expressed in this form. Again, it's nothing but the scalar product of two. One is E1 hat x derivative of u, E2 hat y derivative of u, E3 hat a z derivative of u. Scalar product with differential E1 hat dx1, E2 hat dx2, and E3 hat dx3. The scalar product of these two expressions will lead to the total differential of the potential energy. We defined this first factor by the gradient. It is a three-dimensional slope that is a vector gradient operator. We conclude that the force is the force here. You find force times the displacement as a scalar product is a minus total differential of the potential energy. And what we have found is this is nothing but minus the gradient of u dx. And this dx is arbitrary. So for any arbitrary displacement, both sides must be the same. That means a force is minus a gradient of the potential energy. The force is along the direction to which the potential energy decreases. No increase. Decreases most. A scalar field is a function of position. Field in physics, it is not a field in mathematics. Field in mathematics is just like a real number when you define an algebra, but we don't care about this mathematical fields. Electric field, gravitational field, that are physical fields, and in physics, field is a function of position, and position stands for the three-dimensional space coordinates, something like that. We remember the Cartesian coordinates, it's a derivative with respect to another Cartesian coordinates, follows the simple rule for the polynomial. If the two Cartesian coordinates are identical to each other. If it is not the case, for example, y coordinate and x coordinate, they are independent. But partial derivative of x with respect to x is 1, something like that. X, y, z are x1, x2, and x3. In many cases, when we learn something in high school, we preferred to use x, y, z. But now we must be familiar with x1, x2, x3, which one is much easier to memorize for general purpose. We apply the gradient operator to x squared. What happens? X squared is by Pythagoras' theorem, sum of square of Cartesian coordinates, and gradient operator is x component is x derivative, y component is y derivative, and z component is z derivative. And this guy applies to this one only, and these two vanishes. This y derivative has only a single non-vanishing contribution out of x2 squared. A z component, this. As a result, the final result is just sum of these. What's that? X squared's derivative is 2x. So as a result, we have a factor of 2, and remaining piece is just nothing but the position vector x itself. Next, we apply this gradient operator to the magnitude of a vector, the position vector, and magnitude is the square root of a scalar product of itself, so x square root x squared. Now, this is a complicated function. This x squared, x vector squared is a square root, x1 squared to x2 squared, and x3 squared. So we'd like to make a chain rule. Let this guy, we rename this one as f. So square root of f. How can I do this computation? For example, chain rule. And then, okay? So this should be partial derivative. So this one is 1 over 2 square root of f, and this is x1 squared only. You know, x2 squared, x3 squared does not contribute to the derivative with respect to x1. Therefore, we have this one is, what's that? 2 square root of f, 2 times x1. 2 cancels. So x1 over square root of f. And originally f was this, Okay, square root of f is nothing but the absolute value of x. As a result, we have this one, these two to cancel to this x1. So x1 divided by absolute value of x, e1 hat, x2, e2 hat divided by absolute value of x, and x3, e3 hat divided by absolute value of x. What's that? This is x divided by the absolute value of x. What's that? That is unit radial vector in 3 dimensions. In a similar manner, we can compute the gradient of 1 over r. This is a very, very useful function that appears in the electrostatics and the gravitational force. We again make use of the fact make use of this kind of chain rule. And the derivative for this is much easier than that, the square root. What we have is just this 1 over x derivative 1 over x squared. So this is over a factor, and remaining piece is the gradient of the absolute value of x that we have obtained, this one. As a result, substituting this result, what we find is this. In fact, if I multiply negative sign on both sides, then x divided by x cubed equals minus gradient 1 over x. Usually, we use radius r to be the absolute value of the position vector. So it becomes unit radial vector divided by r squared is minus the gradient 1 over r. This is the fundamental relation for the inverse square law. Any gravitational force or electrostatic force due to a mass at a point-like mass or a point-like charge will generate the force up to a constant of strength. The geometric form states that the strength of the force decreases proportional to the 1 over distance squared. That is called the inverse square law. That's it for today. Thank you.